Hi, I'm Kevin Kundert with RCAP, the Rural Community Assistance Partnership. Today we're looking into the operation of a horizontal pressure filter to remove radium and iron.
My name is Bob Rick. I'm with Great Lakes Community Action Partnership, a regional partner with RCAP, Rural Community Assistance Partnership. Godley is a small community in northern portion of Illinois, population 400. We were brought into some of these communities initially for technical assistance, and then we get into how they're managing their system and how they're financially managing their system as well. They're currently a groundwater source with radium issues. They brought RCAP in to help them build a regional project. They had some potential to bring surface water from the Kankakee River and build a treatment plant, but they wanted to get a partnership with the surrounding communities so they can build what they're calling a water alliance, so that these small communities could get off of the groundwater and the radium treatment and then go to a surface water treatment plant.
The source of our water is 2 deep wells, about 900 feet down in the St. Pete's aquifer. What's unique about the source water is some of the characteristics would be high in radium. To remove the radium and hydrogen sulfide, first off we aerate the water, and then that goes to atmosphere to where it settles some of the iron, and then when it comes through the plant we have an HMO system, which is Hydrous Manganese Oxide. That removes the radium, and then we backwash that out of our pressure filter. We have a 3-cell pressure filter that runs 300 gallons a minute. That removes the radium, and then we chlorinate it and we add polyphosphate. So this is our well 3. We have 2 deep wells. This is well 4, our deep well. Well 3 is our emergency well. Both of them are 900 feet down. They're both triple cased all the way to the pump. And then our static level on it is about 380 feet. So we always have 400 feet of water over our pump. We pump it down about 200 feet. So we usually have about 150 to 200 feet of water over our pump. Our formation comes from the St. Pete's aquifer. 500 feet to 900 feet, this aquifer has about 20 picos of radium in it. This is our aeration with our detention tanks. It's rated for 300 gallons a minute. The water comes through the top, it free falls down through some media. The media breaks it up, it accumulates some of the iron, and the rest settles in the bottom of the tank, which we pump out every year. We shovel it out. From here it goes directly into the treatment plant, right into the vessel. Our 20 horsepower service pumps draw from this, and our 50 horsepower wells fill this. And the water comes in through here, it comes in through 2 20 horsepower service pumps. From there it gets pre-chlorinated, and then we add our HMO, our Hydrous Manganese Oxide. From there it goes through our 3-cell pressure filter. The pumps create the pressure to push it through the treatment. On the back end we add post-chlorination, and then we add polyphosphate. From there it goes to distribution or into the storage tower. So here's HMO, Hydrous Manganese Oxide. It's got to stay mixed 365 days a year or it hardens up. This is a 3% solution, so it's 3% HMO. This is our bulk tank, which we get delivered, and then we pump it to our day tank. Here's our day tank, same thing, 3%. Here's our HMO pump. It pumps from our day tank up to here. This is our carrier pump. It creates up to 7 gallons a minute. The water pumps up this way, makes a Venturi effect, siphons that HMO right into here. It's blended that way, goes right out, 7 gallons a minute into our filter. That's how we remove the radium. So here's our chlorination, gas chlorine. These are the tanks we have in use. These are our full tanks, and our empty tanks would be over there. These are the scales, so it's showing we have 27 pounds left. We use about 1.5 pounds a day, so 1 tank gets us, 4, 5, 6 months. Up here is our hydro valve. On the computer is how we turn up or down the chlorine, And you can do it manually in here, but instead of coming in here risking chlorine, we can just do it right from the computer. So here's our chlorine leak detection for chlorine safety. We have a detector down there. Once it detects any parts per million of chlorine, chlorine's 2.5 times heavier than air, so chlorine gas falls. Once that detects chlorine, it sends this up. Once this hits a 0.2, it sets an alarm outside. We get the alarm. When it hits 0.5, it automatically closes. It sends the signal to here, it energizes a battery, it closes all of our robo controls, so then the chlorine leak either goes away, it opens this exhaust fan, we vent it out, we get the alarms. Of course, we wait till it says 0, we put our mask on and we come in here and find out where the leak is. So this is our polyphosphate skid. It's sequestered ortho polyphosphate. We use about 4 to 5 pounds a day, which is about 1/2 gallon per 50,000 gallons. We shoot for an orthophosphate reading of about a 1.2, and then that basically makes sure we have a layer over all of our mains so we don't have any lead and copper issues. It helps with our corrosion plan, and it helps for the aggressiveness of the water. So here's our polyphosphate barrels. This would be for fluoride if we need to start doing fluoride. These are the scales. This is how we monitor it. Polyphosphate, we're mixing a 3-to-1 blend, so it's 3 parts water, 1 part poly. That weighs about 9.59 pounds per gallon, so that's how we dial it in. Our distribution system is about 7 miles in total. We have 6-inch, 8-inch, and 10-inch mains, all C9000, so all plastic. Storage, we have a 200,000 gallon tank. It's 186 feet tall. Our minimum water level is 149, and we keep usually halfway full, so we keep about 90,000 gallons in the air. Up to 120,000 we keep just to get our 3-day storage. This is our solenoid panel for our pneumatic valves. This is where the pneumatic valves are. Each one has it gets an electric signal to energize the solenoid, and then the air compressor opens, charges that line, and opens these valves right here. So in the event that it's not working in auto, we can manually energize those solenoids and open the valves that we need open during our backwash. These are our AWI valves for air wash and fluent valves. These are what, when we do a simu-wash, we use air. And then when we do a restratification, we use air. That breaks all the stuff up, it restratifies the filter media, and it repacks the gravel to the bottom so we could get a good drain. All right, so this is our PLC panel for the SCADA system. It shows our detention tank, it shows our elevated storage. The first sequence of operations would be the elevated storage. It tells the plant when to start, it tells the plant when to stop. It gives us low alarms, so we can set a low alarm if something's not happening, it tells us. The well pumps, same thing. It's got a PID, so it's trying to get the wells to fill our detention tank as fast as we're emptying the detention tank into the water tower. It shows our filter manual, it shows what's open, what's closed. We can, if it's not working in auto, we can put it in manual, manually close the valves. There's 3 cells, each cell does 100 gallons a minute. It's rated at 300 gallons a minute. Our HMO set points is for our flush duration. When the HMO shuts off, we can flush the HMO skid, and that prevents anything from hardening up inside. Our detention tank settings, when it hits 6.8, it shuts the well off. When it hits 4.0, it shuts the service pump off. So here's our effluent flow meter that tells us how many gallons per minute is coming through the filter, and then it sends a signal to the flow on the wall, and that tells us how many gallons a minute is going to the water tower. This is a sensor probe that tells us how many GPM. So when we're backwashing, we know how many gallons a minute we're backwashing. If we're filling our tower, we know how many gallons a minute we're filling our tower, and we know how many gallons a minute we need to set our well to fill the detention tank to be in sync with what our water tower is filling from our service pumps. So that's our finished water. We got four labs, so this is our raw water, influent before the filter, effluent after the filter, and then this is what's going right to the water tower. So you fill it up to the line, you zero it out, and this is a total chlorine test. Put it in there. And then you wait 3 minutes and you hit read. So when we do our test, it shows your total parts per million of chlorine. It shows the date. We test it daily. Once we test it, we put it down. We write down the results, and then we take a picture of it. If anyone ever had a question of what we tested that day, we could look back and we can timestamp, you know, this test was this day, taken at June 14th, and then you can zoom in and you can see June 14th, 1.66, 1.66. We test everything in the lab, and then we go on site to distribution and verify that what's on paper is happening in the distribution. So we have to keep our minimum residual levels so that we verify in the system. You know, every day is a challenge. You never know what you're going to come into, and every day you learn something new and you're helping people out.
For more information on RCAP training materials and resources, go to rcap.org.